Welcome back to Calculus 1. This is part 2 of our lecture on the chain rule, and we're going to immediately jump into several examples. All right, now example 1, which was in part 1 of our lecture, was pretty straightforward, about as straightforward as it gets. Make sure you're comfortable for here, all your functions, viewing them as composite functions, f of g of x. And if you can do that, apply the idea of divide and conquer, differentiate your outer and inner functions, and then you can combine your pieces together with the chain rule, f prime of g of x times g prime. Now, the first two parts, A and B here, are on the simpler side, so I'd like you to pause to make an attempt at parts A and B. Parts C and D go together, and we'll wait till we go through that so you can see what's similar but different about parts C and D. So pause, give yourself an attempt at least at parts A and B, and we'll check in several minutes. All right, welcome back. Let's go through the first two parts. So our first step to apply the chain rule is we need to identify our given function as a composite function, f of g of x. So we'll identify our outer and inner functions as the outer function f of x equals x to the fifth, and the inner function g of x equals 1 plus e to the x. All right, we can easily calculate these functions' derivatives applying the power rule and then basic exponential rule for its derivative. The derivative of e to the x is itself. Now we have all of our pieces here. We just combine them back together with our chain rule here written in red. Make sure you're comfortable realizing we use f and g several times throughout applying the product and quotient rules. Now we're using the same notation, but for a very different meaning, a composite function. So it should be clear from the context of the problem how the pieces f and g are combined. Here, f and g are combined as a composite function. All right, so we just plug our information into one another, g of x being plugged into f prime. We get our derivative here. F prime of g of x, that becomes 5 times 1 plus e to the x raised to the fourth power. And then g prime, e to the x, is what we're multiplying by at the end there. Okay, and the last version there written is just rearranging some of the factors, pulling the factor of 5 and e to the x out front, just to clean it up a little bit. All right, let's take a look at part B. This one is maybe just a little more unfamiliar, since exponential functions, a topic in pre-calculus, maybe that was a while ago. So we're going to look at our exponential function. The input is up in the exponent. So notice in the outer function, f of x equals e to the x, your input variable is up inside the exponent. So we'll identify the exponent, 2x plus 3, as our inner function, g of x, and the outer function is the exponential function. All right, differentiate each piece. That should be straightforward. And we just have to now combine our pieces using the chain rule, f prime of g of x times g prime. All right, hopefully you're getting a sense for how divide and conquer works. Identify your outer and inner functions, calculate your respective derivatives, and then combine them back together. All right, let's take a look at parts C and D together. All right, this one is probably the more straightforward of the two parts, parts C and D. Notice inside of the sine function is x squared. So we'll say our inner function, g of x, is x squared. And on the outside is the sine function, f of x, we'll define it to be sine of x. All right, now it's only just getting a little more complicated since we need to be familiar with trigonometric functions and their derivatives. Ideally, you know all 6 trig functions and their derivatives at this point in the course. And we know the derivative of sine is cosine. And we just have to combine the 4 pieces back together here. F prime of g of x times g prime. All right, and we get our answer for the derivative 2x times cosine of x squared. Again, that's coming from plugging g of x squared into f prime cosine of x. That's where the cosine of x squared comes from. That is your f prime of g of x term. All right, now part C is a little more straightforward. Part D is probably only more complicated due to being unfamiliar with the notation for powers of trig functions. So make sure you're comfortable rewriting sine squared of x. Make sure you're comfortable rewriting that as sine of x, that quantity squared. And now it'll make it very easy to identify the outer and inner functions, which individually are the same functions from part C. It's just your outer and inner functions are switched. Here, our inner function for part D is sine of x, and the outer function is now x squared. And make sure you pause to at least understand it. This is similar to part C, but our outer and inner functions have been switched, comparing part C to part D. All right, now if we complete the problem, calculate the individual derivatives, it's the same work, but we just get a different end result because different composite function here, the outer and inner functions were switched compared to part C. If we use our new pieces here, combining them together, we should get as our derivative 2 sine of x. That's plugging sine of x into f prime. Just replace the x in f prime with sine of x. And then we multiply by cosine of x, which is the derivative of the inner function, g prime. All right, so we get our derivative here as 2 sine of x times cosine of x. Okay, so that concludes this example, example 2. The problems are starting to get a little more complicated. And what I want to do before we get to example 3 is point out some, I guess, similarities between the outer functions and the various examples we've looked at. We've seen powers of x a lot and exponential functions. And that's going to lead to 2 special cases of the chain rule, which we're going to summarize. And it's going to make basically the more complicated problems a little bit easier. We're kind of getting to the territory of now, given a function, calculating its derivative might involve applying multiple differentiation rules. Maybe the chain rule with the product rule, maybe the chain rule several times in succession. Problems will start to get complicated, so we might want more efficient tools than divide and conquer. Divide and conquer could be very tedious for the lengthier problems. All right, so let's take a look at these 2 special cases. These are going to focus on 2 very common outer functions. Typically, frequently encountered outer functions could be a power of x, x to the n, or an exponential function. All right, and the first one is kind of building off of our basic power rule, which was for x to a power, or x raised to a number. But the general power rule deals with a function raised to a power. So instead of x to the power, we get a function to a power. All right, now if we apply the chain rule, we differentiate the outer function, which is written in red there. The outer function here, f of x, is x to the n. The derivative of x to the n would be n times x to the n minus 1. And if we combine our pieces using the chain rule, we get this expression for y prime, n times g of x raised to the n minus 1th power. That's your f prime of g of x term. And then with the chain rule, we always multiply by the derivative of the inner function. Here it's g prime. All right, now this is again building off of our basic power rule, which was for x raised to a power. The general power rule here is for a function raised to a power, which we've seen several examples a lot. This is just meant to kind of speed up how we would answer those questions. Okay, let's take a look at a very brief example just to illustrate how we would use this, the general power rule. So let's say we have a function y here defined as x squared minus 2x plus 3 raised to the 4th power. Now you can apply divide and conquer here, but it's a lot more efficient to now use this special case of the chain rule. So the general power rule is the chain rule. It's just a tailored version for functions raised to powers. All right, now to calculate the derivative y prime here, we take the power 4, bring it out front, keep the inside the same, but subtract 1. So 4 minus 1 gives you the exponent 3 there. But then at the end, we multiply by the derivative of the inner function. And if you differentiate x squared minus 2x plus 3, the derivative of that part inside the parentheses comes out to 2x minus 2. Notice we didn't identify the outer and inner functions. The general power rule already does that for you, where the outer function is x to the 4th here. All right, there's another special case. This is referred to as the general exponential rule. This is going to be used frequently throughout the calc sequence. And the exponential function, we know its derivative. The derivative of e to the x is itself e to the x. Well, what we're looking at now is not e raised to the x power, but e raised to a function. And we write that here, y equals e raised to a function g of x. Okay, now we apply the chain rule, differentiate e to the x, the outer function. The derivative of e to the x is itself. If you plug g of x into that, for f prime of g of x, you get your original function. F prime of g of x is just e raised to the g of x. But because we are applying the chain rule, we multiply by the derivative of the inner function. The inner function is what appears in the exponent, g of x. Its derivative, we write it just as g prime of x. All right, and this we'll be using very frequently throughout some of the examples throughout the next few lectures. All right, let's take a look at a very brief example applying that. Let's say our function is e raised to the negative x squared. All right, what the general exponential rule says, we get the original function back. That's your f prime of g of x term, and the derivative of e to the x is itself. So our original function comes back, e to the negative x squared. The only thing we need is the inner function, negative x squared. We just need to calculate its derivative. And the derivative of negative x squared is negative 2x from the power rule. So we just multiply here, e to the negative x squared times negative 2x. A little more common notationally to put the factor of negative 2x out front. So we get our derivative, y prime here, without using divide and conquer, identifying the outer and inner functions. Again, the general exponential rule here, a special case of the chain rule, does that for you. So we get as y prime negative 2x times e to the negative x squared. Where did the negative 2x come from? That is the derivative of the inner function. The inner function here is negative x squared. All right, now definitely pause copy these special cases down into your notes. They're going to be helpful for the examples we'll be getting to, where we might have to, in addition to applying the chain rule, apply the product and or quotient rules with that. Some of the other examples we'll be getting to in the third part, we might have to apply the chain rule several times. These special cases are meant to make those more difficult problems as simple as possible. So pause, copy these down if needed, and then we'll get to another example. All right, when you're ready, let's get to example 3. Okay, so the examples are getting progressively more complicated. Example 1 was about as simple as it gets. Example 2, a little more complicated. Example 3 here, a little more complicated yet again. Okay, now all 3 of these examples, you can apply those 2 special cases, the general power rule and general exponential rules. I'd like you to make an attempt at these, but they do be a little challenging. This is our first time applying several differentiation rules all together. So make an attempt, give yourself maybe 2 to 3 minutes. If you find you're just getting stuck, unpause, resume. We'll go through these together then, but try to make an attempt, since I bet many of you feel comfortable trying to apply the chain rule here. Try to use the general power rule and general exponential rule. All right, let's go through part A. And what we're going to use here is one of our biggest tips, not only for this question, finding the derivative of a function, but probably one of the biggest tips throughout the entire calculus sequence. Before you do anything, just try to rewrite your function. All right, let's rewrite 1 divided by the square root of x to the 4th plus 1. We can rewrite that as x to the 4th plus 1 as a negative 1/2 power. The 1/2 power is coming from the square root. Notice the square root is in the denominator, so we can think of this as x to the 4th plus 1 raised to the negative 1/2 power. Now, if you differentiate that rewritten version, it should be very easy to differentiate applying the general power rule. We have a function raised to a power. See if you can apply the general power rule to complete this question. We'll check in maybe 30 seconds. Okay, let's apply the general power rule. So we take the power, negative 1/2, we bring it out front. We keep the inside the same, but we subtract 1 from that exponent. Negative 1/2 minus 1, that becomes negative 3/2. All right, what we also need is the derivative of the inside. We need the derivative of x to the 4th plus 1, which is 4x cubed. Okay, and that basically does it. This we can rewrite. Notice you have a factor of 4.5. That cancels out to leave you with a factor of 2. And we can rewrite the negative 3/2 power as a power or factor in the denominator. So we get this alternate version for the derivative. Maybe it looks a little cleaner, which we'll be using for one of our last examples, being able to rewrite it all back as a fraction. Okay, let's move on to part B. This one, we're going to be applying the product rule, since we have x times an exponential function. Now, all the examples within this lecture involve the chain rule. Where does the chain rule get applied here? Well, notice that factor or second function, e raised to the negative 3x, that is a composite function. So we can apply, in addition to the product rule here, we have to apply the chain rule, and we can apply the special case of the general exponential rule. So if you were stuck seeing how to apply that here, calculate f prime and g prime. G prime, you can use the general exponential rule to find it, and then you just combine your pieces back with the product rule, since we're identifying the f and g of x here as the factors. All right, if we calculate these derivatives, f prime should come out to be 1. The derivative of x is 1. And if we apply our new special case called the general exponential rule for differentiating e raised to a function, the only thing we really need to know is what is the derivative of the inner function. And that derivative comes out front. So the derivative of negative 3x is just negative 3. So for g prime, we get it as negative 3 times e to the negative 3x. That's how we're going to be using those special cases. Here, we're applying the product rule, but while applying the product rule, we need to apply the chain rule to find g prime. The general exponential rule speeds that up a little bit. Okay, if we combine our pieces back together using the product rule, we get our answer here, which can be simplified. Notice you can factor out e to the negative 3x from each part. And you get a very nice simplified derivative here. All right, when you're ready, we'll take a look at part C, which is probably one of the more complicated examples so far in the course, since we're applying the product rule and the chain rule, maybe in a different order than what we've done already. When you're ready, let's get to part C. All right, now this one does get a little complicated, so we're gradually building up how difficult the problems are. All right, and notice here, we have two different sets of parentheses. We're multiplying them, so we can identify this function y as a product. So we'll identify f and g as the individual factors there. So we'll say f of x is x squared plus 1 cubed, and g of x is x cubed plus 1 squared. What I'd like you to do is differentiate f and g, and you can do that using the general power rule. Since our functions here are functions raised to powers. All right, so see if you can calculate f prime and g prime using the general power rule. We'll check in about a minute. All right, let's apply the general power rule. Notice the exponents are coming down. And we multiply by the derivative of the inside for each of them. For f prime, the derivative of the inside is 2x. And for g prime, the derivative of the inside is 3x squared. All right, before advancing, make sure you're comfortable with those two calculations. Both of them, we apply the general power rule, which I have written there. All right, and that is pretty much most of the work, at least at the level of calculus, calculating derivatives. But for us here, this is going to be a good example for us to kind of practice our algebra skills. The final answer can be simplified considerably, as we're about to get to. So let's rewrite f prime and g prime. We'll just clean that up a little bit. We're basically just multiplying the factors of 2 and 3 to get 6. In the first function, f prime, we get 6x. In g prime, we get 6x squared as the factors out front. All right, and we'll just combine all the pieces here now using the product rule. F prime times g plus f times g prime. All right, and this turns into a big mess. So just make sure you're comfortable where all the pieces come from. They're all written above. And we are going to simplify this, but we're not going to simplify it by multiplying this out. That would probably take me all day, and we don't want to do that. Nobody's got time for that. So our alternate way that we're going to simplify this is, notice there's lots of common factors. So instead of multiplying this out, we're going to simplify it by trying to factor this. All right, and if you take a look at your common factors, we have some common factors of 6x, x squared plus 1, and x cubed plus 1 as common factors. Now, between those common factors, you can always factor out the smaller power. So we're going to factor out from both terms, that's to the left and right of the plus, the addition sign, 6x times x squared plus 1 squared times x cubed plus 1. Now, if your algebra skills are top-notch, you should be very comfortable with this. If you're having difficulties with this factoring out here, your algebra skills could be brushed up a little bit, but this is a good problem to practice that. All right, so let's factor out 6x times x squared plus 1 squared times x cubed plus 1. And what's left, I'm putting it in brackets. Notice from to the left of the addition sign, we're left with a single factor of x cubed plus 1. And to the right of the addition sign, we're factoring out 6x, so we're left with one factor of x. And we're factoring out x squared plus 1 squared, so we're left with x squared plus 1, just a single factor of that. And notice this result here looks pretty simple. We can clean it up a little bit. Inside the brackets, distribute that x through the parentheses, and then you have some like terms that you can simplify and combine together within the brackets. So we get our simplified derivative here basically just by factoring it rather than multiplying it out. All right, and that's about as simple as we can write the derivative here for y prime. All right, now example 3 here, the problems were getting a little more complicated. Most of them only required us to apply 2 differentiation rules, product rule with the chain rule. Within the next and final part, part 3 of our lecture on the chain rule, we'll be getting to some more complicated examples, example 4 and 5, where I might have to apply the chain rule multiple times.